So regions in the plane, that's what we're going to look at today. In a way, it's still looking at inequations. The difference is, with an inequation, you were just talking about what can the x value be. Whereas regions in the plane, we're saying, what could the x and y be? So when we draw a region, it's the same idea. We would draw the boundary first. So when it was just an equation, we'd find the critical point and we'd plot that. Same idea, but now we're going to find the curve and draw that. How do we draw it? Again, we have to indicate, is it included or is it not included? So with an inequation, we had an open circle or we coloured the circle in. So when we go to the number plane, we use a dotted line to show that it's not included. So if it's just less than or greater than, but a solid line if it's equal to as well. So that's how we tell the difference. That's why when you draw your asymptotes, you always dot the asymptotes, because we're saying this is not included. This line is not part of a possible solution. We might have the situation where lines intersect. So how do we deal with that? Well, if the point of intersection is not included, then we use the open circle, same as we do with the inequation. When does that happen? Well, basically, if one of them is a less than or a greater than. So in other words, if one of the lines is dotted, then we would have an open circle. So if they're both dotted, we would still have an open circle because one of them is. But if they were both solid lines, then the point of intersection is included. Some people like to draw a solid circle. You don't have to when they're both solid, but that's just a matter of preference. Then, again, just like the inequations, what we would do next is we would test a point. We'd say, oh, does it work for x equals 0, and so on. Same idea, but now we test a point that's not on the curve. But always make it easy for yourself. The origin is the first one you try because both the x and the y are 0, unless that happens to be on the boundary, so then you can't test it. But a y-intercept, an x-intercept, those sorts of things. So let's start with a simple one. Straight line, y is less than x plus 3. So the first thing we do, draw the boundary. This one will be dotted. And so, whoop, there we go. There's the line y equals x plus 3. I still label it as y equals x plus 3 because that is the equation of the line, but dotting it tells us it's not included. Which side of the line are we? Well, I need to test a point. As I say, the origin's not on that line, so that's an easy one to substitute in. So let's test that. 0 is less than 3. Well, yes, it is. So therefore, we must include it in our solution. So our solution is on the right-hand side there. We don't have to have straight lines, of course. So here we've got x squared plus y squared greater than or equal to, in this case, 9. So hopefully we recognise that to be our circle. We'll draw it in. It's solid because the boundary is included. So now we've broken up our number plane once again into two bits. We've got the inside of the circle and the outside of the circle. So I'll test 0, 0. 0 is greater than or equal to 9. Well, no, it's not. So therefore, I must be on the outside of the circle. By the way, you don't have to colour it in like mine's nice and solid. Usually we just draw like lines to indicate, okay, this is the region I'm talking about. This is an interesting one. Y is less than the square root of 4 minus x squared. So again, do you recognise it? It's a semicircle. Radius of 2, centre 0, 0. Positive square root, so it's the top half. It's dotted because it's just less than. So let's draw it in. There it is. Now at this stage, you'll notice it doesn't really separate the number plane into sections, because imagine if a point was just buzzing around, it could sort of come around the bottom and then head back in. There's nothing separating the two. So something special happens here. I'll test a point, first of all, to see whether I'm inside the semicircle or outside the semicircle. 0, 0. Yes, 0 is less than 2. So I know 0, 0 is included, but that's not the solution. And so the x-axis is not a boundary. So there's nothing stopping points falling out, if you like. we still have to consider the domain of the function. See, it's only possible for points to exist in between -2 and 2. So we have like a corridor between those 2 points. Now, every point underneath the x-axis is true because they would have a negative y value. And a negative is always going to be less than the square root of something. So they're all included, but I can't go past 2 or on the left-hand side -2 because I wouldn't be able to substitute in the x value. It's not in the domain. So that's why we sort of have this corridor. But notice this. It's actually solid there, not dotted, because any point on that line underneath satisfies the inequation because the y value would be negative. And so, yes, the negative would be less than the square root of 4 minus x squared. So I think one of the big mistakes people make is to dot that corridor. But there's also one other thing I have to do. We said when 2 boundaries meet, if one of them is dotted, we circle the point of intersection. So therefore, I should be circling those x-intercepts. And just to confirm that, substitute in the point 2, 0. Look what happens. We get 0 is less than 0. Well, no, 0 is not less than 0. It's actually equal to 0. And so that point is not included. Now, if that was a greater than instead of a less than, we'd still have those corridors, but now the corridors would be going up from the x-axis instead of down. So that's just one function by itself. But what happens if we have multiple functions? So in this case, I've got y is greater than or equal to x squared and y is less than or equal to 3x plus 4. Well, y is x squared. I know that's to be a parabola, so I'll draw that in first. So there's our parabola. Y is greater than x squared. Am I inside the parabola or outside the parabola? Well, let's test a point. I can't use 0, for this one because it's on the boundary. So I'll just pick some point, probably on the y-axis. I can pick any point I like. So I'm going to use 0, 1. Substitute that in, and I get 0 is less than or equal to 1. Well, that's certainly true. So I know I'm inside the parabola, but I don't shade it in yet. What I do is I'll just mark some crosses or some sort of thing so I know I'm inside the parabola. Now let's look at the other one. Y is less than or equal to 3x plus 4. So let's draw that line in. It's also solid. The other thing we need to find as well, the point of intersection. We should be labelling those points as part of our solution. So, all right, I might do that first. Solve them simultaneously. X squared is 3x plus 4. All right, so the left-hand point of intersection must be -1. The right hand would be x equals 4. So let's label those. -1, 1, and 4, 16. So back to checking the line. Which side of the line are we on? So let's use 0, 0. 0 is less than or equal to 4. Yes, it is. Once again, I'm not going to shade. I'm just going to mark in and say, all right, now I'm on this side. But notice I use different colours because all I really have to ask myself, do I have both red crosses and blue crosses? Well, we can see clearly where that is. So let's shade that section in. But I haven't finished yet. You'll now notice I've changed dotted lines there because the boundary is just that part that I've shaded in. So where the line extends out, that part of the line is not included in the solution. So I dot it. And the same with the parabola. After I get past that region, that's not included in the solution. So I dot it. And we end up with just that little section there with solid lines in this case. So exercise 3F, just a handful of questions there.